Hi everybody. Well, we have been talking a lot about a joint inverse of a matrix, that too square matrix, and therefore in the last lecture what we studied, that was a result, very important, is going to be applied now in today's lecture. What was that result which we visited in the last lecture, which holds a great deal of importance, is this particular result, that A, where A is a square matrix, A is any square matrix of order n. So what is A? Is not just any random matrix, it is a square matrix of order n. A is invertible. You know what is the meaning of invertible? If and only if A is non-singular. You remember this result that we did in the last lecture? We also proved it, and I told you this is very important. Its importance will be revealed in today's lecture. Why is it important? How is it important? What is its application? And if this would not have been there, what all problems would have occurred? What all were the questions whose answers you would not have been able to obtain? All these things will be clear to you in today's and the upcoming lectures now. So here a square matrix of order n, A, is invertible if and only if it is non-singular. This particular if and only if that you can see over here is something which is making this statement greatly important. Because of this if and only if, there are two aspects or two conclusions related to this result. First conclusion and second conclusion. First conclusion is that whenever in your journey of matrices you see that there is a matrix which is invertible. So I am saying A is invertible. Suppose there is a square matrix of order n which is given to you as invertible. That means you are given that there exists a matrix B. There exists a matrix B which is again a square matrix of order same as that of order of A, such that A into B is equal to B into A equals identity matrix of order n, where n is the order of A and order of B. So A is invertible is given to you. You are given that A is invertible, you already know that A is invertible, that means you know that definitely there is some B existing for which A into B equals B into A equals identity matrix of order n. Then you can very nicely say that this implies A is non-singular. This implies A is non-singular. The moment you are aware about this fact about a square matrix A of order n, you can conclude about this fact also holding for the same matrix A, that A is non-singular by this result. Non-singular means that determinant of A is not equal to 0. Is it understood? Now, if A is invertible, this implies A is non-singular. Now, in here, if I try to mold this statement a bit, it means that the moment a square matrix of order n is singular, it cannot be invertible. If it is invertible, it has to be non-singular. If it is singular, it cannot be invertible. So this is automatic conclusion that A is singular. That means determinant of A is 0. A is singular implies A is not invertible. Implies A is not invertible. Is it understood? So this conclusion leads to this conclusion automatically, right? The other conclusion which is being derived from this statement is the converse part, that A is non-singular. Suppose you have a square matrix of order 2 or of order 3 which is not having its determinant to be equal to 0. That means when you have computed its determinant by the approaches that we know, the determinant is not coming out to be 0, it is coming out to be a non-zero quantity. So if you have a square matrix of order n such that determinant of A is not equal to 0, this definitely means that A is invertible. A is invertible. Definitely. Now A is invertible means definitely. If A is given to be non-singular, definitely there will exist a matrix B which is of order same as that of A, such that when you multiply B by A in both the ways, A into B and B into A, these both results are same and they are equal to identity matrix of order n. What is that B if you are aware about A being invertible? If you are so sure that A is invertible, The moment you have this fact given to you that A is non-singular, if you are so sure that A is invertible, what do you think is the guarantee of the existence of matrix B? If you are saying that A is invertible, that means you are guaranteeing that there is a matrix B which is existing such that A into B equals B into A equals identity. But the question is, how will that B be computed if you are just aware about the fact that determinant of A is non-zero? How will that B look like? Okay, how are you going to get to the very matrix B of order n, which is same as the order of A, such that A into B equals B into A equals identity? And the answer is what? So A is invertible means there exists B such that A into B equals B into A equals identity, matrix of order n, where this matrix B with the help of matrix A and this fact that determinant of A is non-zero can be computed in what way? You just need to consider this scalar 1 upon determinant of A. This is a scalar, it is a real number because the denominator is not equal to 0. The moment the denominator is not equal to 0, 1 upon determinant of A is a non-zero quantity. It is a non-zero scalar. This is what? A non-zero scalar. And consider this matrix. Then you have scalar times adjoint of A matrix to be coming out to be equal to matrix B such that A into B equals B into A equals identity. This is what is called the inverse of A, and this exists only when A is non-singular. So these two conclusions we had derived from the result that A is invertible if and only if it is non-singular. What is the relevance of this result? What is the relevance of this result? We are going to now begin with this new section, which at a point is going to use this result drastically. Okay, what is that particular article? The article is, now we have to understand what do I mean by solution of simultaneous linear equations. Solution of simultaneous linear equations. Either you can have m linear equations in n unknowns, that means 5 linear equations in 4 unknowns, or 7 linear equations in say 8 unknowns. Either you can have this category in which number of equations is not equal to number of unknowns, or you can have the other category in which number of equations is exactly equal to the number of unknowns. That means you have n linear equations in n unknowns, m linear equations in m unknowns, right? In what is the sense that I am saying this in? I am saying that you have 3 linear equations in 3 unknowns, 5 linear equations in 5 unknowns. These are two categories to be studied separately. What is our basic motive is, our basic motive and the demand of our syllabus is to be knowing about computation of solution of system of equations such that you have m equations in m unknowns. That means that scenario or that case in which number of equations, linear equations is equal to number of unknowns is what our venture is to study. So we are not going to focus our attention towards that particular system of linear equations in which number of linear equations is not equal to number of unknowns. Rather, our entire attention would be on the class of those systems of linear equations, those systems of simultaneous linear equations in which number of equations is equal to the number of unknowns. So it is solution of, I should not write this, it better should be solution of system of, because there will be a system of simultaneous linear equations, or I should write simultaneous n linear equations in n unknowns. So I would not be again and again specifying, but our entire attention would be upon this itself, that how many ever linear equations you will be having, those many unknowns you will be having. Clear? Solution of system of simultaneous n linear equations in n unknowns. So there will be a system, that means more than one linear equation will be occurring at one time. So simultaneously, suppose 3 linear equations will be occurring in 3 unknowns. Fine, and our venture is, our task is to basically be able to compute the solution of that entire system. How does a system of linear equations, simultaneous linear equations, which are n in number in n unknowns look like? Let us take n equals 3 and understand it through this dummy example. I am saying consider the system of three linear equations in three unknowns. Generally it is going to look like what? So the three unknowns are x, y and z. I don't know the value of these three unknowns. I have three equations in these three unknowns. So first equation is a1x plus b1y plus c1z equals d1. This is first equation in three unknowns x, y and z. a1, b1, c1, d1 would be known to you. They will be numbers, they will be known to you. Next equation is a2x plus b2y plus c2z equals d2. This is the next equation in the same three unknowns x, y and z. And then you have yet another equation a3x plus b3y plus c3z equals d3. This is the third equation in the three unknowns x, y and z. So this is equation 1, equation 2, equation 3. This completely is one system of three linear equations in three unknowns x, y and z. This completely together simultaneously considered is one system. This is one system. All three of them are belonging to one system. If I have to find a solution, I don't have to find the solution of one equation, I have to find the solution of the entire system. Solution of this entire system means what? Find out that value of x, y and z which on being plugged over here satisfies equation 1, on being plugged over here satisfies equation 2, on being plugged over here satisfies equation 3 as well. That means solution of not one equation is supposed to be found. I have written solution of system is supposed to be found. That means that value of x, y and z we have to find which satisfies first, second and third all three equations of the system. If there is a value x, y and z, a value of x, a value of y, a value of z which are the three unknowns which satisfies this first equation and second equation but fails to satisfy the third, or satisfies the second and the third fails to satisfy first, or what I am trying to say, it satisfies any two but fails to satisfy the third one, or satisfies any one fails to satisfy the other two, it is not a solution of the system, it is a solution of that individual equation or of those two equations, but it is not a solution of the system. It will be called a solution of the system when it has the power to satisfy all the equations in the system. We have to not focus upon finding solutions to one or two equations, we have to focus our attention towards finding solution of the entire system and the ways to find it. So this is my system of three linear equations in three unknowns. What we are going to do is, right now you can see no contribution of matrix or no look of matrix or determinant coming in here in picture, but of course we are doing this chapter matrices and determinants, so obviously somehow I will have to connect this particular article to matrices to determinants. How do I do that? What you do is, just before I formally try to brief you towards understanding a matrix approach towards this concept, I would ask you to consider something. Consider a matrix A which is a 3 cross 3 matrix. This 3 is for what? This 3 is for number of equations and this 3 is for number of unknowns. How many linear equations are there? 3. And how many unknowns? 3. Now what you do, pick up these constants a1, b1, c1 coming from the first equation a1, b1, c1, like this you keep. Then you have a2, b2, c2, correspondingly you keep a2, b2, c2. Then you have a3, b3, c3. So correspondingly you keep a3, b3, c3. Whatever these constants are. Consider this matrix A. Also consider a matrix B which is 3 cross 1 matrix. What is this 3? Number of equations. Okay, here what will come? D1, D2, D3. Consider a matrix X, which is again 3 cross 1, but here 3 is what? Number of unknowns. So inside this matrix, unknowns will come X, Y, Z. So you can see, with the help of this entire data, I have just segregated this data in 3 fashions. I have collected the coefficient of X, Y and Z from 3 equations, and I have created this matrix A. So all the coefficients of X, Y and Z have been kept intact over there in a very nice fashion. The first column is coefficient of X from all the 3 equations, second column is coefficient of Y from all the 3 equations, third column is coefficient of Z from all the 3 equations. Okay? Now that I have kept all the coefficients of X, Y and Z over here in this fashion, then I pick up these constant terms and I create a matrix of order 3 cross 1 and I name it matrix B. I am just left with these unknowns X, Y and Z, so I collect these X, Y and Z and create a matrix X of order 3 cross 1. If you now just consider A into X, is A conformable with multiplication with X? See, A is a matrix of order 3 cross 3, X is matrix of order 3 cross 1. You can see number of columns of A is equal to number of rows of X, and therefore A cross X exists as a matrix of order 3 cross 1. This is order of AX. Okay? Is order of AX. So clearly A and X are conformable for multiplication. A is what? A1, B1, C1, A2, B2, C2, A3, B3, C3. And X is what? X, Y, Z. You know how to multiply? If it is a 3 cross 1 matrix, I know it has 3 rows and 1 column. In the first row will come what? What will be the 1/1th entry? Then there will be 2/1th and there will be 3/1th entry, because it is a 3 cross 1 matrix. So 1/1th, 2/1th and 3/1th. 1/1th will be interaction of first row with first column. So first row of this and first column of this has only 1 column. I will be multiplying this with this. I will have A1 into X plus B1 into Y plus C1 into Z. A1 into X plus B1 into Y plus C1 into Z. Then I will have the 2/1th entry, which will come as a result of multiplication of second row here and this column here. So it will be A2X plus B2Y plus C2Z. A2X plus B2Y plus C2Z. And then the 3/1th entry will come as a result of multiplication of third row here and first column here. So it will be A3X plus B3Y plus C3Z. It is already given to me that A1X plus B1Y plus C1Z is equal to D1. This is equal to D2, this is equal to D3. So what I am getting here is, as a result, what I am getting here is that because A1X plus B1Y plus C1Z is D1, I will be replacing it by D1. A2X plus B2Y plus C2Z is D2. A3X plus B3Y plus C3Z is D3. And this matrix I have called as B. Right? This matrix I have called as B. So I am getting AX is equal to B from here. This is implying that AX is equal to B with this A, this X and this B. And if I begin with AX equals B, what do I get? If I am beginning with AX equals B, what do I get? AX equals B, that means A1, B1, C1, A2, B2, C2, A3, B3, C3, X, Y, Z. You know that this multiplication is going to produce a 3 cross 1 ordered matrix, and B itself is equal to also of order 3 cross 1. Clear? So this makes sense. Just multiply this, you know this is what? A1X plus B1Y plus C1Z, A2X plus B2Y plus C2Z, A3X plus B3Y plus C3Z. This is a 3 cross 1 matrix and it is equal to this 3 cross 1 matrix. Whenever two matrices of same order are equal, that means their corresponding entries are same. So 1 1th entry here will be equal to 1 1th entry here, 2 1th here will be equal to 2 1th here, 3 1th here will be equal to 3 1th here. So this implies that a1x plus b1y plus c1z will be equal to d1, and along with it a2x plus b2y plus c2z will be equal to d2, and along with it a3x plus b3y plus c3z will be equal to d3. So all these three will hold. 1 1th will be equal to 1 1th, and 2 1th will be equal to 2 1th, and 3 1th will be equal to 3 1th. That means this equation will hold, this equation will hold, and this equation will hold. All these three will hold simultaneously. That means this entire system will start establishing. So what I am trying to say is, another way of writing the system of equations, 3 equations and 3 unknowns, is with the help of this matrix equation. In a very short way, you can write this entire system of 3 equations and 3 unknowns in the form of this one line matrix equation Ax equals b, where you know how A will be formed, how x will be formed, and how b will be formed. Okay? So that is how, if you have a system of 3 linear equations and 3 unknowns, I can very nicely, very feasibly convert this system or write this system in the matrix form with the help of matrix A, matrix B, and matrix X. So we have considered this and we saw that Ax equals b was nothing but another alternative fashion of writing the same system of linear equations, in whichever 3 in number and in 3 unknowns they were, and that is why we are able to say that if this is a system of 3 linear equations and 3 unknowns, then if you consider this as A, this as B, this as X, then if I say this system is star in the matrix form, can be written as Ax equals b, where A is this, B is this, X is this. Clear? This matrix A is called coefficient matrix of the given system of equations. Okay? Why coefficient matrix? That's but obvious, because over here we have kept the coefficients of x, y, and z in a certain fashion. First column is coefficient of x from all the 3 equations, second column is coefficient of y from all the 3 equations, and third column is coefficient of z from all the 3 equations. So A is called the coefficient matrix of the given system of equations. So either I write this system like this, or I write Ax equals b, where A is this, x is this, b is this. It is the exact same thing. We just understood it from here, right? So here Ax equals b was considered, A is this, x is this, b is this. When we solved it, we eventually got this system. If you begin from this system and you consider this as A, this as x, and this as b, when you multiply it back, you get Ax equals b, right? So therefore, in order to write this complete system in expanded form, we just avoid it, and instead of that, we write the matrix form of this system of equations. Okay? So therefore, if you have a system of n linear equations and n unknowns, you can very comfortably write it in matrix form as Ax equals b, where A will be the respective coefficient matrix of order n cross n, B will be the matrix of order n cross 1, and here in each row there will be just one constant coming from the RHS of every equation. This is the RHS of every equation, and you write the RHS of every equation, which is nothing but constant, to get the matrix B. And then you are going to have another matrix X of order n cross 1, where in each row there will lie an unknown. Is it understood? So therefore, this happens to be our very idea of understanding the system of linear equations. Is it clear? So here, if I just begin with an example. The system of linear equations (2x plus y equals 7), 3x plus 2y equals 9. This is one system. This is one system in two. This is two equations in two unknowns. So this is two equations, two unknowns. Okay, this is two equations and two unknowns. So it is number of equations is same as number of unknowns. Fine. The system of linear equations, this can be written in matrix form. It can be written in matrix form as, how can it be written in matrix form? As Ax equals B, where A is a 2 cross 2 matrix, because 2 is the number of equations and 2 is the number of unknowns. So A is this, where what will be the scenario? First column will be coefficient of x, second column will be coefficient of y. There is no third unknown. This is matrix A, matrix X is 2 cross 1, where 2 is the number of unknowns. Unknowns are x and y. So here it is x, here it is y. And you have matrix B, which is again 2 cross 1, where 2 is the number of equations. From each equation we pick up the right hand side. Here the right hand side is 7, right hand side is 9. Write down, and you have A, x and B. The moment you have A, x and B, you can very easily see that Ax equals B, which is this, is going to give back to you this particular system of equations. Is it understood? So that's how, first thing is how we are going to associate the very venture of finding solution to the system of n equations in n unknowns with matrices and determinants. First step is this, that learn to come from here to here. Learn to write a system of n linear equations in n unknowns in the matrix form as Ax equals B, where A is the coefficient matrix, X is the matrix of unknowns, and B is the matrix of the right hand side constants from every equation. Is it understood? So from here, if you have learned to come here, if you have learned how to come from a system of n equations in n unknowns to writing it in matrix form like this, halfway you are through. Now we are going to just focus our attention on matrix A, matrix B, matrix X, especially on matrix A, in order to conclude about solutions of this system. Is it understood? So we are going to just focus our attention towards this, but if you are not aware about coming from this step to this step, you would not be aware about the matrix A, you would not be aware about the matrix B, and therefore you would not be able to apply the strategy which I am going to teach you in order to compute the solution of the system. So please practice coming from here to here. Pick up any system of simultaneous linear equations in which the number of linear equations is equal to the number of unknowns, so that matrix A, which is the coefficient matrix, comes out to be a square matrix. Because A's order is n cross n, where first n is the number of equations, second n is the number of unknowns. So until and unless both these are not equal, A will not come out to be a square matrix, and I want A to come out to be a square matrix. That is what is in our syllabus. So just keep a very good track of a system of linear equations in which number of linear equations is equal to number of unknowns, and then from here come over here to write it in the matrix form, where A is your coefficient matrix, which is square matrix. Okay, so practice this nicely. In the next lecture I will be talking about certain terminologies which you should be aware about. After that we will be moving to actually finding the solution of the system, first by converting it from here to the matrix form and then working upon these matrices. I will see you in the next lecture. Thank you.